We now turn to the subject of permeability. And permeability is an important topic in soil mechanics. It's also the topic that ties soil mechanics into some of the other parts of the civil engineering discipline, especially those relating to hydrology and definitely environmental concerns. Virtually all environmental concerns involve groundwater in one way or the other. And I think it's important to understand that, what it means. We talk about, in biology, we talk about the biological cycle. And really, we talked in the early part of this course about the rock and soil cycle, which in many ways precedes the biology cycle. And then now we're going to talk about the hydrologic cycle. People talk about a shortage of water, but that's not really true. Water is something that is recycled continuously in the natural environment and in the human environment. In fact, one thing that's been proposed is basically to take, after we treat the sewage to the degree that we do, to take it and just run it straight back into the system. And that has a yuck syndrome to it, yuck kind of association with it. But if the filtration is proper, it can be done. So normally we prefer to put it back in the environment and then take it out of the environment. But the whole thing is cyclic. And basically what water shortages indicate is how we've managed, the cycle isn't moving fast enough to keep up with our demands for it. And some of that is due to the size of the demand, and sometimes it's really a relationship between the size of the demand and the size of the supply. So basically, as you see here, the hydrologic cycles start the oceans, which are the largest, but the oceans themselves, they evaporate. Some of it rains back into the ocean. And then it's condensed into the atmosphere. It goes over land. It rains back down. The lakes evaporate some of it. Other parts evaporate some of it. But eventually, the water, because soil is permeable for reasons we'll discuss, much of the water in the lakes and in the oceans actually seeps into the soil and becomes groundwater. And that's what we're going to talk about. An introduction to groundwater. And groundwater, but water is, and then the groundwater itself seeps back into the ocean also. So there's a continuous cycle with multiple loops in it. The amount of the total water in the earth, which is actually in the groundwater, is relatively small. But the effects of that water are out of proportion to their amount. The permeability of soil affects distribution of the water both between the surface and the ground mass and within the ground mass itself, because it is capable of moving. And then that's one of the first things we're going to see in permeability. Up to now, we've stuck with a hydrostatic system where it just sits there. And now we're going to watch it move. We talked about, and that leads me to the first thing, hydrostatic condition. Much water in the soils can be, for engineering purposes at least, considered, it's all really moving similar. I had to move to get there, but can be considered for engineering purposes to be hydrostatic. And that's what we talked about in the last section on effective stress. And we have a situation where water can be where water's two things. That means two things. One of them is that the pressure is strictly a function of depth, and that we don't have issues that come out of the movement of that water. Now we're going to talk about the water moving. Oh dear. those water levels change. One of the things I kind of touched on with boring logs is the fact that, groundwater is not a fixed level. The phreatic surface is not fixed. It can change with seasonal variations. The structures we put on top of it definitely change groundwater levels. In fact, one of the major challenges of stormwater is the fact that the structures we put on the surface alter not only do they potentially add contaminants, but they also alter that flow. And that can create flooding in places where we had no flooding before. And on the opposite end, that can put places can be dry where they had water before. We have artificial structures, then that can change that. And also, we have a situation, particularly in coastal areas, where well waters and drains draws down. And what happens in many cases is that as we draw the water, if we're in a coastal area and we draw down, the ground actually drops with it. This is referred to as subsidence, and there's a serious problem in coastal areas where, we normally talk a lot these days about sea level rise, but nobody's talking. Before that, we've had to deal with problems of coastal level drop due to subsidence. And subsidence leads coastal areas to more vulnerable to flooding. By taking the water out of the ground, we essentially kind of like a form of compaction where we pull the soil particles together and they drop. Permeability. The definition of permeability is the property of soils that allows water to pass through them at some rate. This property is a product of the granular nature of the soil. Without the granular nature of the soils, or without voids in the soils of some kinds, the water is not going anywhere through it. With that, the water can pass through it. Different soils have different permeability. Some will admit water through them. All of them are capable of having hydrostatic water, but some, and you remember when we talked about effective stress and hydrostatic stresses, we didn't differentiate between cohesive soils with small grains and cohesion soils with large grains. Well, that's because hydrostatic doesn't really affect the hydrostatic. Once we start moving the water, then the different permeabilities, it is largely a function of the grain size, is the most important thing. And we'll talk about that. We talk about Bernoulli's law, and I mentioned, I spend more time in my fluid mechanics level classes on Bernoulli's law. We use it a little differently in soil mechanics. It has three components in both cases: a kinetic component, the first term, pressure component, the second, and gravitational, the third. It's an energy balance of the soil as it flows through the ground. Normally speaking, because of the water flow through porous media like this is relatively slow, we ignore the kinetic effect. In other words, it's there, but it's not really important to us. So, for example, a 1 foot per second velocity only produces about a 0.015 feet of head difference for the water. And you'll notice already we've got head difference. We're also going to ignore losses in the soil. You remember, some of you having fluid mechanics lab, we talked about head losses in pipes and orifices and stuff like gate valves and stuff like that. We're going to ignore those as well. The problem, the tricky part of soils is that, and part of the reason why we're going to ignore those is because water flow through soil is slow. If it's fast, then you've got serious problems because you've probably got some erosion going on. But we want to talk about something called, through a pipe, we talk about we have flow, and then we divide flow by area to get velocity, an average velocity in the pipe or in the orifice or whatever. In the case of specific discharge, is the way we do it with soils. And it's a little different. basically the velocity, but it's kind of the same, is that the specific discharge is equal to the Q over area. It's essentially the same thing as the velocity. The problem is, the reason why it's called specific discharge as opposed to velocity is because we have, if we've got a free fluid with no obstructions in it at all, just maybe friction on the side, then you've got, the average velocity is in fact the flow divided by the area. With soils, you've got all these little grains in there, and we could go through a bunch of rigmarole and try to figure out what these specific, what the velocity is. But what we do instead is we come up with an average velocity for the water, ignoring the fact that the pores are there, is basically what we're doing. That may sound like a strange concept, but it's simpler from a mathematical standpoint, and we're going to use that to get our point across. Another thing we want to talk about is, I don't throw a lot of things at once, is hydraulic gradient. Hydraulic gradient is equal to the change of head over the change of length. And you'll notice that the head at any point, like I said before, is a function of the pressure and the gravity. Most all water flow we're going to talk about here is driven one way or the other by gravity in the soils. Hydraulic gradient is an important concept because as the water moves through the soil, its head is going to change. And that head is going to change. And obviously, the longer length that it takes to change, in other words, the longer length it has to flow, then the hydraulic gradient will drop because the length lengthens. So the hydraulic gradient is an expression of the change of head in a given length of flow. And Voigt goes into a differential formulation, which may be of interest to some of you. It's probably not of interest to a lot of you at this stage. But like I said, underground flow tends to be driven by gravity, and you can see that by this by this diagram. The water table in this case with this aquaclude, which is a aquaclude. Let me just make a few definitions. An aquaclude is what is where the is what actually prevents water from flowing through it. An aquifer is something that carries water or holds water. And therefore, we've got this aquifer between aquacludes, and basically the water flows down through this curve in kind of a one-dimensional way, although it takes a little, it doesn't take a perfectly straight path, but a very gently changing direction. And the head at the top of this thing and the head down here is going to be different. As you go down, your gravity head is going to the energy is going to transfer from basically gravity to pressure, and that's going to be that change of head basically drives what your of static head, that is. A change of static head is when, and we're talking about static head, we're not talking about dynamic head or anything like that, we're talking about static head, is what changes, is basically driving it. The water in this aquifer is not only sitting there, but it's actually moving downward by gravity. Darcy's law, interesting, that's the monument to him. Was come up with a Frenchman named Darcy. It should be spelled differently if you want proper French spelling. Darcy was commissioned to design and build a fountain in the city of Lyon, and he came up with this law about water flow through soils. And the water flow, basically what he said was that the water flow through a soil, or the specific discharge, now here we go, that specific discharge, now we're going to use it, which is the Q over the A, is equal to the coefficient of permeability, K, which define, over times the hydraulic gradient. In other words, the higher the hydraulic gradient for a given soil, the higher the specific discharge. For a given hydraulic gradient, the higher the permeability of the soil, the higher the specific discharge, and vice versa. If we multiply both sides of the equation by the cross-sectional area, we get the flow, and we get KIA, which is the area. There are some assumptions. The biggest, soil saturated, is one of them. The other one is that you have laminar flow. We normally don't, if you've got turbulent flow in soils, like I said, you've got problems, which go past the issue of permeability. So, and generally speaking, laminar flow exists when, if you can keep your hydraulic gradient below 5 and your Reynolds number below 1, which, as you know from fluid mechanics is low, then you've got laminar flow in soils. So, in any event, there's where you use your specific discharge. You're able to actually, K encapsulates the whole issue of, granular size and whatnot, and other factors, and angularity and all that fun stuff, and enables you to use the specific discharge to estimate flow. The coefficient of permeability, in theory, he says, well, how do you figure it? Well, that's been one of the challenging issues of geotech from the get-go. It is equal to the kappa, which is the physical permeability, times the G, which is the gravitational constant, over the dynamic viscosity of the fluid. It can also be the unit weight over the kinetic viscosity times the kappa as well. Either way, either formulation works. I explained that in fluid mechanics lab too. And absolute permeability, however, the physical or absolute permeability is only really significant if, this is where the environmental part comes in, if we have something flowing through the ground other than water. I mean, like gasoline or some other noxious stuff is flowing through the ground. For geotech purposes, we're not going to spend a lot of time on absolute permeability or physical permeability of the soil, because water is the only fluid we're really going to think about. Now, if your environmental situation is different, and what will happen to you is that different fluids will flow through the soil at different rates depending upon their physical properties, their viscosity, either their dynamic viscosity or their kinematic viscosity and unit weight. So keep that in mind. There have been many attempts to figure out. One of them is the Cosine-Kármán relationship, which goes back a long ways. And basically it is a function of the dynamic size of the soil particles and the porosity. Now it makes sense that, the more porous the soil, the easier the water will flow through it. But getting from that obvious to the to the reality of trying to make it figure has pretty much it's eluded. So it's good for a qualitative, but to figure it is no. We also have the seepage velocity, which basically takes the specific discharge and divides it by the porosity. It's an attempt. I mentioned earlier that it's difficult sometimes to get a handle on the actual velocity of the fluid flowing through. The seepage velocity is an attempt to do that on on a fairly simplistic level. It's interesting, and it shows the importance of the porosity, like the cosine-carbon relationship does. But ultimately, we don't normally use it. But what we do use is what we use in a more convenient way in practical application is we use the K based upon the type of soil and the characteristics of the soil. And you'll see here in this crappy looking chart, I've got better looking charts down the road, where we actually, in this chart, which is from the Bureau of Reclamation, we actually show the relationship between the classification of the soil and the possibility of K, and the range of K that we can expect. And that's important because, as you know, classification is in turn based on grain size and void size. So we talked about in capillary rise. And as a result, a soil that would have a very fine grain will have very low permeabilities, and with ones with large grains have very high permeabilities. And Veroit's little quick and dirty chart here in the corner illustrates that perfectly. Notice that K is in units of velocity. That's just the way it is, and get used to it. But instead of going through the rigmarole of cosine, carbon, or whatever, we use K, and we usually determine it experimentally. Notice also that the ranges of these things are large. Not only within themselves, for gravel, for example, we have 10 to the minus 3 times, that's a difference of 100. But also, look at the difference between gravel and clay, or even sand and clay. 10 to the 5 difference, 10 to the 4 difference between the two. That's an amazingly wide range, order of magnitude. You don't see that very often in many of the other physical sciences on a specific topic. It makes permeability the hardest, because of that nature, it makes the permeability one of the hardest quantities to actually nail down in soil mechanics. And in fact, it is the most difficult and is the most subject to error in terms of our use of the physics. Let's take a quick one-dimensional example, because Darcy's law is expressed in terms of one dimension. Now you say, well, how much good can that do us? Well, and one of the things you're going to find out in soil mechanics is that we're really good at expanding the nature of our problems without making the math break down on us completely. So let's just river and canal, which are parallel to each other. The delta H, which is the difference in physical height between the two, is 5 meters. In other words, either the river is 5 meters above the canal, or the canal is 5 above the river. We don't say. The distance between the two, or the length of this channel, there's a permeable channel between the two. And it's that length is 200 meters, that permeable channel. It's a permeable channel under the ground. The thickness of that channel along an area is 2 meters, and the K we're given, the coefficient of permeability, is 2 meters per day. Fine, and you'll see virtually every type of velocity used for K under the sun. So don't just brace yourself. Find the seepage loss per kilometer of river channeling. So we take our basic equation. Q is equal to KIA. I is equal to delta, this simplistically is equal to delta H, which is the distance from one end from the canal to the river. I is the distance this way between delta H is equal to the canal river this way, and delta L is this way. H is what's driving the gravity. So the I is equal to 5 over 200. And since QK is equal to KIA, I know KA is simply equal to the thickness of it. Now here we come to the tricky part. We don't have a width. They didn't tell us how wide this thing was. Well, you are going to find, and this is another concept that freaks students out, that many times one of the simplifications we do in civil engineering is to take three-dimensional problems or two-dimensional problems at least and make them into nice one-dimensional problems. All problems are really three-dimensional. It's just that that's hard to deal with sometimes. We were not told how long this stretch of river and canal is, and we were not told how long this connecting thing under it was either. So we have to say, and since that's the case, we have to say basically, and the find actually gave us the hint, seepage loss per kilometer of river canal length. What we're going to do is we're going to basically assume that we're dealing with a kilometer length. In other words, the width of this thing is 2 meters this way and 1,000 meters this way. Now we compute the Q. First, K, which is 2 meters per day. Plug and chug. Second, I, which is also 5 to plug and chug. The third, the area A is equal to this area here times 1,000. We're going to say it's per kilometer. If it's per meter, it'd be 1. But it's more convenient per kilometer. The real length could be half a kilometer or 2 kilometers. We just multiply it when we want. But the Q, the resulting Q, is 100 cubic meters per day per kilometer of length. You're going to see problems like this where we do per meter of length, per foot of length. Retaining walls are going to be full of this. I mean, that's just the way we do retaining walls, and you just need to get used to it. This is your first exposure to that concept. So how do we determine the permeability coefficient? We've kind of thrown up in our hands, and I think someday, you know, I talked about granular analysis. Someday we're going to be able to simulate the flow of fluids on a practice. You know, they're going to basically run a lot of fluid flow through, and they're going to find what we found experimentally, which is that it obviously is going to vary with the size of the particles and the size of the voids, but it's also going to vary stuff like angularity and all this good stuff. And we may learn more. But until then, we normally use laboratory tests. And laboratory tests we would need anyway in order to verify our computational methods. The biggest ones are the constant head test and falling head test for laboratory. Now, the problem with permeability is that there is no, in addition to being wildly unpredictable, one of the reasons why it is getting an undisturbed sample out of the ground into the laboratory with the same soil skeleton structure, and that's a nice term saying that, you know, the arrangement of the particles being the same in the lab as in the field is very difficult. Very difficult. And that's one reason why permeability is so hard to predict. We have in situ methods, which are good. We're going to talk about some of those. Pumping tests, consolidation tests. We can actually use consolidation tests, which we'll talk about later. But any way you slice it, it's not easy. We're going to talk about the two laboratory tests first, the constant head test and the falling head test. And we're going to explain two things. One, they're important because they illustrate probably most perfectly the whole concept of Darcy's law, at least particularly the constant head test. And the second of all, they're going to answer this next stupid question: why do we have two tests for one property? We're going to see. A constant head test is very simple. You have a water flow through what's called a permeameter. And a permeameter is basically a can usually made out of plexiglass these days, and it has a soil sample in it of a known length, and usually that length is the length between the two piezometers you stick in there and measure the head drop across them, and cross-sectional area and all this good stuff. And you basically flow water using gravity from a tank way up yonder, and you flow it through, and you measure the amount of water that flows through. And permeability you can use in order to prevent additional losses. A lot of times when we have enough flow, then we can use a flow meter of some kind. In permeability tests, it's very common to use the old bucket brigade deal, where we measure the amount of water that flows through at say I collect a liter in a minute or a liter in 30 seconds. That's or even longer than that in some cases. That's pretty much it's practical in this case. And you run it through, you get it out. So these are I take your basic equations and I add a few things. One of them is K20. K20 is the standard coefficient of permeability at 20 degrees C. That's the standard. And with groundwater, it's not going to vary that much. R sub T is the temperature correction. That's in case your water in the lab varies that much from 20, which sometimes it does. The delta H, of course, is the head loss across from the piezometer readings. The delta L is the length of the specimen, which is actually the distance between the two piezometer pores. And then A, the cross-sectional area of the specimen, and the time. Because big Q is the quantity of flow in, say, in cubic centimeters, and the A is the cross-sectional area and the T is the time in seconds, as I just mentioned. So let's give a soil sample, which is 15 centimeters high, and that by high I mean between the piezometer ports, and 5.5 centimeter down round. I've had problems over the years with students who wanted to make them square, but that's what it is. Test results: the measured head across the sample is 40 centimeters. The time of and basically what I'm saying is that it discharges 400 cc's of water in 6 seconds. And we're going to assume the test runs at 20 degrees C, which is not an unreasonable assumption. Our lab, I think, runs a little bit cooler than that. Because it's in the basement, it tends to be cold down there. Find the coefficient of permeability. Governing equation, Q is equal to KIA. Definition of variables in the governing equation. Flow rate, little q, is equal to big Q over T. Well, that's amazing. And then the sample area is equal to pi d squared, for it is round. And the hydraulic gradient, of course, is delta H over delta L. If I do a lot of this stuff and I do some math, I rearrange and I can get K20 out of that using this equation without having to do a lot of pre-conversions. And all I do once I get there is I plug and I chug, and you can and should check this to make sure I'm not just blowing smoke in your face. So that is the constant head permeability test. We now turn to the issue of what happens when soil moves, because that's obviously the whole reason why we're interested in permeability. And we come to the first topic, and the simplest is strictly vertical flow, downward and upward. This is a topic that Buffalo's students and I'm not really sure why it does, but it does. But I think in order to solve it and to understand what's going on, we need to consider, you see diagrams frequently like this, and they don't really tell you what's going on. They put a lot of stuff, but they're hard to follow. There are two things you must do in the beginning of a permeameter problem like this, where if you see it, there are two things you must figure out right up front. The first thing, this is downward flow, and we know it's downward flow because this head level here is higher than this head level here by this h. So, you need to first of all figure out two things. One, you need to figure out the hydrostatic at the surface of this. You need to figure out the hydrostatic head at this surface down here. And this is this difference in head, and this one down here is going to be that difference in difference. Because notice, this is free water here, this is free water there, and the hydrostatic head for free water is strictly equal to z, the distance from the surface down to whatever point, times the head's just z, just that z difference. And basically, if you know that, then you know the difference of head between here, and you can actually compute the flow. Now, what's the difference between downward and upward flow? Well, with downward flow, if you do a little thing, if you think about it, at hydrostatic conditions, it goes, you're not going to go anywhere. And, in other words, the water's not going anywhere at hydrostatic conditions. If you stop and compare the difference between the head from here to here and the head from here down to here, if there was no water flow, you would realize that the head here, if there were no water flow, this head would be greater than this one. Now, obviously, that's not physically realistic, but what it tells us, though, is that basically the downward flow this way, the poor water pressure decreases at the bottom. If the poor water pressure decreases, the effective stresses increase. And if the effective stresses increase, like a case of capillary rise, which is kind of the flip of this problem, then the particles will be drawn closer together. On the other hand, if I have upward or vertical flow, this head is higher than this one, and this goes down here and pushes the water upward. Now, that being the case, I need to know, again, the hydrostatic head here and the hydrostatic head here. And obviously, this hydrostatic head is going to be quite a bit larger than this one, and water flow will flow up. The thing about it is, if I compare the effective stress here and under hydrostatic conditions, basically what this does is that this hydrostatic head is going to be less than this. This actually increases the pool water pressure. If you increase the pool water pressure, you increase the effective stress. If you increase the effective stress, then you're going to get to the point where you're going to increase the pool water pressure where the effective stress is zero, and that's a problem. We're going to talk about that a little bit later, but right at the moment, let's look at this problem here. There's a couple of ways of solving problems like this. The first and simple way of solving this problem is to note that, I'm going to walk you through this, is this. The head here is 3 meters. The head at the bottom is this right here is 13 meters. And basically now, this is important. If you noticed all the effective stress diagrams up to this point, the variation within a layer, the variation in effective stress, the variation in pore water pressure, is uniform, is linear. So the simple way to solve this problem would be to consider that this is 13 and this is 3, and basically by and that's linear. You could basically figure out by linear, you can actually figure out the point at B, and I would invite you to try that. B is 1 meter below the top and 2 meters above the bottom. And by assuming a linear distribution of hydrostatic head, you can come up with the you can actually come up with the head at that point. But again, to do that properly and do it anyway, you have to identify the head, the hydrostatic head here, and the hydrostatic head here. A little fancier way to get to that is the way Voigt. He starts with that equation, which I show you up here in the corner. And if you divide delta P by gamma, you get delta H, which is equal to Z times 1 minus I. Now I know delta H. It is 13 minus 10, which I see over there. I know Z is 3 meters thick. So all I have to do is to substitute, and I can compute the hydraulic gradient, which is minus 2.333. If I take the minus 6.667 from the bottom upward, and I start with 13 at the bottom minus 6.667, I get 6.333, or 6 1/3. If I do it from the top, I go 1 meter, which is using this formula over here, and I get 1 times 1 minus 2 plus 2 is 3.333. If I add that to 3, I get 6.333. I get the same result. So those are the two ways you can use to solve. You've got this method, which is a little more formal and fancier, and you've got the other one, which is a little more informal. But both of them will work. The tricky part is if you've got more than 1 K in there, and things get a little more complicated than that. The last topic for today is falling head test. In principle, I could analyze all my, constant permeability is pretty much a straight up application of Darcy's law. Down to a point, it's fine. The problem is if you get into, very low permeability, you have in clays and silts and that sort of thing, you can't, you'll take forever to get results. To speed things up is a falling head test, and basically what it involves is putting a pad of soil in the bottom and a standpipe. And obviously the more permeable soil is, the faster the water is going to fall from the standpipe. And that enables you to get a reading using very low permeability soils. And the equation we use is this one right here. And again, it's pretty much a plug and chug kind of deal, although you have to rearrange the stuff. The variables are pretty much the same except H0 and HF. And the time is not the time the water flows, but the time that you have a drop between point H0 and last HF. The time between that is the time. So other than that, it's no different. So for example, you have a falling head permeameter. The sample diameter is 2.5 inches. The sample thickness is 1 inch. The standpipe diameter is 1.7 millimeters. Traditionally, standpipes are pretty small. The initial elevation water is 32 centimeters, and 395 seconds later, we stop and we look at the water, and it's 30 centimeters elevation. It doesn't matter, which way, as long as you're using as long as you're measuring it from the surface of the water, you're in good shape. Is the thing about the elevations. They're measured from the surface of the water, as you see in that diagram over there. And we want to find the coefficient of permeability of the clay. And we go through a similar process that we did before, defining some variables, making some substitutions, and we come up with this equation over here, which enables us to do direct substitution of the input quantities, and I get 2.9, just shy of 3 times 10 to the minus 6 centimeters per second, which is definitely a cohesionless soil. So that in a nutshell are those problems tend to be very simple and tend to be very straightforward, which is not necessarily the case with upward and downward flow. But in any event, that pretty much concludes our first session on permeability. Thanks for watching, and God bless.